Sure. Let's start. Last lecture, we completed with type 4 Black-Scholes question as well. Now, in order to just give a broad overview of the chapter of what we studied in Black-Scholes option pricing model, we first started with looking at the introduction. So we understood, let me just draw on this part itself. We understood that we had studied our binomial model, which was a discrete option pricing model. We realized we needed a continuous approach. We needed a continuous version in order to price my options. Hence, we realized that there is my Black-Scholes option pricing model that I'm going to study. But before that, because I'm now transitioning from a discrete model to a continuous model, I need a framework, I need a process, I need a model in order to fit or in order to predict my underlying asset price. For that, we understood our Brownian motion, wherein we understood this is that process, this is that framework, whom I can use in order to predict my underlying asset price under a continuous framework. In this, we understood standard Brownian motion, general Brownian motion, geometric Brownian motion, so on and so forth. We then needed a framework in order to differentiate or integrate this particular process or this particular Brownian motion. Hence, we studied the chapter of Ito's process, wherein we had Ito's lemma and Ito's integral. And finally, we went on to understand Black-Scholes option pricing model. Now, under Black-Scholes option pricing model, we first understood the introduction, whatever we are going to study. We started with the assumptions of Black-Scholes option pricing model and we looked at the limitations. We then went on to understand all the concepts that I needed in order to study, in order to solve the sums of this particular model, of this particular framework. So we derived the classical Black-Scholes option pricing formula under call option, under put option for non-dividend paying underlying assets. We then realized that this is not the final equation, this is not the first or the final equation that they derived. Hence, they started with the partial differential equation approach. We started understanding the PD approach under discrete model. We then moved to the continuous model for the dividend paying and non-dividend paying underlying asset. Here, the main issue with the equation or the main issue with the framework was the call option was being priced in terms of its own option Greeks. And I know in order to calculate my option Greeks as well, I need my option pricing. I need an option pricing model. Hence, it became an infinite loop. Thus, the final equation or the model that I generally use in practical world as well is the first equation that we derived, which is a Black-Scholes option pricing formula. We then we went on to understand the different kind of questions that we'll have. We saw type 1, type 2, type 3, type 4. Type 1 is straightforward formula-based questions, wherein we understood the most easiest kind of questions. We'll have one parameter unknown, on parameters known. You need to find the unknown parameter. If it's not the call option or the put option that I'm pricing, it can be any of the inherent implied parameter, your S, K, R, sigma, T, whatever. We realize the starting points, we realize the minimum number of tries, maximum number of tries. Type 1. Type 2 question was exotic option, under which, again, the most easiest kind of type. We realized there are two ways of solving this. The first type is we can express our exotic option or our exotic strategy in terms of my simpler plain vanilla call option put option. Second type is I use my truncated log normal distribution in order to price my strategy. That was type 2 kind of questions. We then looked at type 3, which was the Greek derivation. We derived the delta and gamma for a non-dividend paying call option. I shared a PDF with you all which has the derivation for all other Greeks as well. Two types of question. Either they can ask you to derive or they can ask you to, again, like type 1, all parameters known, one parameter will be unknown. In this, except for delta, all other equations will be given to you in the question. You're not expected to remember any of the Greek except delta for a call and put option. That I think because it's straightforward, it may not be given. But all other Greeks, the equation will be given to you in the question. May it be derivation, may it be application. That was type 3. We then finally looked at type 4, which was look back option. We named it as look back option, but we used the equation of distribution of maximum value. We did the sum price of the option at time 0, price of the option at time 1, probability that the maximum value of HT, so on and so forth. We used that particular equation in our last lecture. Any doubts? Anyone in the chapter? Solve नहीं किया अभी तक time नहीं मिला. All right. I know we just completed last week. Y'all can continue. Y'all have a lot of time with y'all. Start solving. Whenever y'all start solving any type of questions, y'all have any queries, y'all can reach out. Or y'all can raise it during lecture. That's fine. So that was the type of questions under which we have our Black-Scholes framework. Now, as I said, because we were so done in our last lecture, there's just one last small concept that's remaining. Again, this is a concept that you all already know. It's not a new concept. While doing the assumptions, I'd actually done this concept. The concept is called as implied volatility. That's the title or the category that I'm giving. Now, if you'll remember during when we were doing the chapter during the assumptions limitation stage, I told you all that the main aim or the maximum work. This is lacking. Just give it a second. Uh, So if you'll remember during that stage, I told you all that the maximum work, okay, but take the maximum work is happening for you all also. Right? You can see. Just give me a second. Let me shut this and open this. Let's see. My laptop doesn't want to work today. So this works. Fine. Now it should. Yeah, focus. So as I was saying that when we were doing the assumptions and limitations, we realized that the maximum amount of work, the maximum amount of effort doesn't go in applying Black-Scholes model, because that is something that even you all did. I was given all the parameters. If I have to calculate the price of my call option put option, I just need to apply the equation that is already set, that is already derived. I just need to use normal algebra calculus in order to derive my call option put option price. Practical life, we've done the volatility smile, that graph that we said. I told you all it's a 3-dimensional surface. It's a two-step interpolation that's performed. So the maximum work goes in getting this value of sigma. The sigma, the parameter that is there in a Black-Scholes model, the maximum amount of effort goes in calculating that particular value. Now, there are two ways of doing this particular part. The first way I can calculate my volatility is through something called as historical volatility. Now, what do I mean by historical volatility? Let's say if I have my option on USD INR as a currency, it's a foreign currency option. It's on USD INR. Now, I know if I have to price my option, if I have to price this option on USD INR, I need the variance, the volatility of USD INR fluctuations of USD INR FX rate. The most natural thing comes to mind is I'll take the last 5 years of USD INR FX rate. I'll use the normal probability statistics equation of variance and compute my standard deviation. That's my volatility parameter. That is nothing but historical volatility. You take the actual historical data, you take the actual time series data, you take the actual data of the underlying asset, and you calculate how much has been the variance, how much has been the standard deviation, how much has been the volatility in that historical data. That volatility that you derive based on this approach is called as your historical volatility. Obviously, this is backward looking. Why backward looking? Because I'm assuming that the same movements, the same variations that have come in the past are going to replicate, are going to repeat themselves in future. Hence, it's kind of a backward looking parameter or backward looking metric. Computer, let me just write using actual historical data. Any doubts with historical volatility? Anyone? Fair. The next kind of volatility is called as implied volatility, and this is what is practically why this is Cool. The other kind of volatility computation is implied volatility. Now, let's see how this is computed. This is what is practically used. This is what is practically computed. Now, can I say in today's market, if I'm looking at Reliance as my underlying asset, let's say, I know in today's market, there are multiple call options, multiple put options of Reliance that are getting traded on the exchange. I'll have a Reliance call option for the next 1 month, 2 month, 3 months, 6 month, 1 year, 2 years, so on and so forth. I'll have it for different strikes as well. I'll have one call option for 1,000 rupees, 1,200, 1,300, 900, 800, 700, 1,500, 1,400. I have multiple strike prices call and multiple time to maturity calls, as well as I'll have the same put that are getting traded on the exchange. Can I say for these exchange traded currency options or exchange traded options, I'll have the corresponding exchange traded price? Because everyone is trading on them, everyone is buying and selling them continuously. Based on demand and supply, there'll be certain exchange traded price for these particular options. Now, can I say if I apply my Black-Scholes model on this, I have the price, I have all my parameters, sigma is unknown. I can backwork for the parameter of sigma, exactly what you all did in type 1. You all have the price, you all have all parameters known, only sigma is unknown. This approach of calculating sigma from already traded options is called as implied volatility. You don't have any underlying asset price data. You all are not taking any actual data. Instead, you all are taking a dump of what are the actual options, what are the actual prices of these options that are currently trading in the market. Based on this prices, I backwork using my Black-Scholes option pricing model to get the value of sigma. And then this is what I can correspondingly use. So I'm not taking any historical data over here, any backward looking data over here. Instead, I'm taking the actual data that is currently trading in the market, that is currently present in the market. Everyone understood? Anushka, any doubts?
Yes, so means in the implied volatility, we use the present data of the options prices.
Exactly. You take the actual option prices that are computed based on demand and supply. You take that prices to be your price of the Black-Scholes model. You have S known, R known, T known, K known. You calculate your sigma parameter. So that will be the volatility of Reliance for that particular strike, for that particular time to maturity, whichever option you've taken. So you take like hundreds of such options of differing values of strike prices of differing time to maturity. So you get the entire volatility surface. For 1 month option with 100 strike price, what is the volatility? For 1 month option, 200 rupees strike price, what is the volatility? For 2 month option, 100 rupees strike price, what is the volatility? 2 month, 200 rupees, what is the value? So as such, you create your entire volatility surface over here for different levels of maturity and different levels of strike prices. Because you'll have the price of everything from the exchange. You have everything, you backwork for the sigma parameter. Understood? So
Yes.
perfect. On an everyday basis, multiple such options gets traded and multiple such calculations happen. Now, what tenors to take, what strike prices to take, those are defined by organizations already. They choose those specific strike prices, those specific time to maturities, and they create that entire volatility surface. This volatility is called as implied volatility. It's computed based on actual option prices. What else? They are forward looking. They're not backward looking because I'm not taking any historical data. These options are going to mature in a future time period. Therefore, I'm taking a forward looking view, or I'm taking a forward looking volatility aspect. I think, yeah, that's it. This was the concept. Let me know if you have any questions. As I said, no one is going to ask you anything specifically directly in terms of theory. But
Can you
we've
give
already
a
seen
live example for this implied volatility? Can you give a live example of this implied volatility?
live example meaning. You will need the specific licenses in order to access this surface. I mean, I have the surface, but they're all company IP.
Oh,
And I don't think you'll get the surface directly available anywhere. It's published by Bloomberg, Murex, Calypso, Reuters, Refinitiv. Yeah, value you will not get anywhere in the public domain. Like the actual values that gets used. Yeah. Let me know once you're done copying.
Sir, in PTSA, we learned that in the weak form of market, you can't use the historical data to predict future prices.
Hmm.
And here we are using that historical data to predict the volatility of the future prices. Means ultimately we are understanding ultimately we are understanding what is the price of the option in future.
Yeah. Because you are
So
currently valuing your option. So in the first scenario, historical volatility, you assume that history is going to repeat itself. So whatever has been the historical trend is going to repeat itself in the future as well. That's the assumption that you take in the first part.
okay.
Like if Reliance has 20% variance or 20% volatility for the last 5 years, in the next 5 years as well, the volatility will remain 20% only is what the assumption is when you do that particular approach.
That is, it is like a Markov process, simplified volatility.
No, no, not there's no Markov or state spaces over here. How is it forward looking? So what you are doing, Ria, you are currently taking all the options. The options are going to expire on a future time period. Therefore, their price today is actually reflecting their possibility of future expiry or future exercise, no exercise. Based on that, the relevant volatility value gets computed. So when you are computing the 1 month volatility, you are essentially saying that for the next 1 month, the option price that is derived based on an assumed or an implied value of volatility of the underlying asset price. That is why it's a forward looking. Like you're not assuming that all these options are going to expire today. These prices actually reflect their future possibility because they have time value as well. They're actually representing the future possibility or the future variation in my underlying asset price, because only then HT minus K minus HT will get priced appropriately. So that sigma parameter, because they are all future expiring options, the volatility or the implied volatility gets computed is a forward looking metric. Understood? Any other questions? Done copying? All right. Let's start with the new chapter then. The name of the chapter is Probability Measure and Risk Neutral Price. I'll write it again fully. I would call it as 5-step discrete and context. I'll write the name of the chapter again. All right. So, as written, the chapter is as part of IQ syllabus objective. It's called as Probability Measure and Risk Neutral Pricing. It's called as Unit 2 chapter, or I mean, it's a part of Unit 2 chapter 2. Now, uh, let me also write the other name. As part of IFOA syllabus objectives, this chapter is called as 5-step discrete and continuous model. Cool. So, till now, guys, as I said last lecture, we are done with all significant or the most heavy kind of chapters that we have as part of our FE. The next two chapters, which is this chapter and the next chapter, are fairly like a supporting chapter for all the previous chapters that we've done. They're a bit of fairly straightforward, given that you'll have understood the previous chapters. A bit of independent chapters, but using the outputs or the inferences from all our previous chapters as well, like your share price process, geometric Brown motion, so on and so forth. So till now, we are done with unit 1 entirely, unit 3 entirely, unit 2, chapter 2 was remaining. This is what unit 2, chapter 2 is. And then the last chapter is a unit 4 single chapter that we have, term structure of interest rates. Now, this chapter that we have, there are two objectives that will satisfy in this particular part. If you'll remember in our Black-Scholes model, when we started with the assumptions, I told you all that DST, which is our SD form of the geometric Brownian motion, we had actually written this as RSTDT plus sigma STDBT. And you'll asked a question, where did R come from? Because the Black-Scholes model or the share price process that we've understood is DST is equal to mu STDT plus sigma STDBT. This is what we derived under our Ito's lemma chapter when we did share price process as a special case. This is the equation we derived. But under Black-Scholes model, this equation somehow became from mu to R. And I'd said that anything in this chapter about share price process that you do, all the parameters mu will become R. In this chapter, we'll actually understand how did this happen and why did this happen in the first place. So the first objective is going to be to understand how did my share price process transition from this equation to a risk-free rate based equation, the equation that we finally used in my Black-Scholes model. That's the first objective of the chapter. The second objective or the second part that we'll understand is, I'm going to write a statement. So, side cash. EPV of the pair. Let me know once I'm done copying. I'll explain you all the second objective. EPV is expected present value. Payoff into probability to P factor. Every derivative payoff can be replicated using 5 shares and psi cash. Price of the derivative is EPV of the payoff. Everyone saw that recording? The missing lecture on 24th Jan. Basically, the derivation of Q. Is that part done? Bas. That's it. Not like we are going to use it. I just want to use that to explain the objective. What else are the doubts from the doubt solving? She sent me one. How many sums were you all able to cover?
3, I guess.
Jill took it, no?
3 or 4.
It was more of doubt creating session.
She didn't introduce it.
Sorry? Okay, let me complete this and the next chapter, then I'll only take a few sessions.
we are more accustomed to your style. No? The style of a different person is different. That was basically notations. Everything is different. Sometimes take it for granted. I mean, actually, doubt clearing sessions and faculty should be same, not the other different. The style of explaining will be different.
Yeah.
Otherwise, it is okay. But only thing is that it's not like, it's not very easy. These subjects are not very easy. Also know our background, can in a better position to explain.
Fair. I think I'll be done in like 2 to 3 more lectures with the syllabus. Then we'll take doubt solving, sum solving sessions. Which chapters did you cover? First chapter. Because the doubt she sent me was of the first chapter. Cool. The second objective, as written. Now, if you'll remember the binomial model, the second chapter ideally, we did 2 approaches, replicating portfolio approach and risk neutral probability approach. Under replicating portfolio approach, what we were doing? We are creating an external portfolio, a second portfolio of shares and cash, such that the payoff from this second portfolio and my derivative portfolio is equal, may it be an up move, may it be down move, may it be multiple time steps. I was equating my payoff by changing the value of phi and psi. From this approach, or from this equation, we actually moved to risk neutral probability approach, wherein we started with this as the derivation and we proved that the price of the derivative is actually payoff into probability into PV factor. That equation wherein we derive the equation of Q. So we had started originally with my replicating portfolio approach itself. From my replicating portfolio approach, I then came to my equation of Q, and hence the inference of the conclusion that price of the derivative is actually payoff into probability into PV factor. So can I say the journey from first statement to second statement is already done? We've already proved that if I can replicate the payoff of the derivative using shares and cash, then ideally the price of the derivative is actually EPV of the payoff, or the expected present value of the payoff. This is something that I've already proved. In this chapter, what we'll try to understand and what we'll try to conclude is whether this statement is actually true. From the first to the second part, we've already done the journey. We'll now try to prove whether the first part is actually true in all sense. That means we'll try to derive, we'll try to prove, we'll try to infer whether all derivative payoffs can actually be replicated using shares and cash. That is what we'll understand in this chapter. That's the second objective. All right. You all can write this down if you all want. I'll just write the contents that we'll understand in this chapter. So we'll start with jargons. We'll go to CMG theorem. We'll go to MRT theorem. And we'll zoom out. We'll do 5-step derivation under discrete under context. So you are able to access LMS now? Got the project? Not yet. It'll come by Monday then. Yesterday they were going to upload. They were like yesterday or max by Monday. See. I think by Monday they should upload. Cool. As I said, the contents of the chapter, or the way the number of concepts that we'll do is, first we'll understand jargons. Except for 2, there are 5 total concepts. Except for 2, the 3 are very straightforward. They are not jargons. Let me call it as jargons and concepts, therefore. The next thing that we'll understand is CMG theorem. It's called as Cameron-Martin-Girsanov theorem. I'll write the full form when we do it. After CMG theorem, we'll do MRT, which is Martingale representation theorem. Once that is done, all these concepts are going to boil down in a single derivation. So it's called as 5-step derivation. Literally, it's called 5-step because there are 5 steps to the derivation. So we'll look at this derivation. We have it under discrete scenario, we have it under continuous scenario. It's just a notation change that happens in discrete and continuous. There's no significant change. Hence, we'll do both of them in parallel. The first objective of the chapter, which is mu to r, we'll complete it till CMG theorem. MRT theorem is an additional thing, and the second objective of the chapter is what we'll prove under the derivation. Cool. Or you can note this down if I want. I think fairly complete the chapter also. Just note this down, whatever we have. Then let's start with the jargons. I'll have R na after this. Not very heavy. If you'll have sustained Black-Scholes and all that, especially teaching from me, this will be easy.
CMA theorem. What is CMA?
It's called as Cameron Martin Girsanov. I'll write it when we do it, but it's called as Cameron Martin Girsanov. Girsanov. And MRT is called as Martingale representation theorem. MRT is Martingale representation theorem. CMG, this is Emma. Should have typed it for this. It's Cameron Martin Girsanov theorem.
Cameron or Cameron?
Cameron. Cameron.
I think that James Cameron, that same surname.
I think that these are 3 separate guys. Done? Right, let's start with the jargons then. Alright, let's start. So, as I said, these are certain concepts, these are certain terminologies that we'll use throughout the chapter. So, beforehand, we'll try to understand what these different concepts or terminologies are. So, the first terminology is called as tradable asset. So, any asset let me write the definition. Any asset that has unlimited buying and selling along with complete divisibility.
Sir, what is it?
So-
Where are the-
Sorry,
What is it?
tradable
Once
asset.
again, that was tradable asset.
Tradable asset. All right. So any asset that has these two properties, first there is unlimited buying and selling. By unlimited buying and selling, I basically mean there is complete liquidity. At any point, if I have to buy the asset, there is a seller available. If any point I have to sell the asset, there's a buyer available. So any asset that has unlimited buying and selling capabilities, along with, this is a theoretical assumption that you can hold that in fractions as well, decimals as well. There is complete divisibility of that particular asset. Such an asset is referred to as tradable asset in theory. Fair enough. All right. I can copy this down. The next one is not, it's ideally an assumption which we already know. It's not a concept as well. But just to put it out clearly, it's called as cash account. It's an assumption that I already know that cash is going to accumulate or discount at the risk-free rate. This we already know that whatever will be the cash component, whatever will be my investments, whatever will be money is going to get accumulated or discount at the risk-free rate of interest. Practically for this, I don't know if I've told you. So for Sonia, Toner, I've mentioned these curves, right? So practically, it's these curves that will be used for any accumulation or discounting. For USD, if I have, then it's a USD SOFR curve. For Euro, if I have, there's a Euro Ester curve. These are basically interest rates, or these are values that are derived based on the actual transactions that happen in the market linked to these particular interest rates. So as an Indian market, as a US market, let's say, all the interest rate related derivatives will have linkages or will have benchmarks to USD SOFR. So based on that trading, I can actually derive my USD SOFR interest rate for the day. So for example, if I and you all enter into a transaction, you all tell me that you all want a fixed rate of 4%. I tell me that I want my cash flows linked to some USD SOFR interest rate, let's say. We'll enter into a transaction. You will pay me, I'll pay you 3% of rate. You will pay me cash flows based on whatever is my SOFR interest rate prevailing in the market. Now, based on our transaction, we can actually compute, based on our demand and supply, there'll be much more transactions that happen. Based on all these transactions, the fixed rate that we are entering into, I can actually compute my SOFR interest rate for that particular day. So we entered at 4%, someone else might have entered at 3%, someone else might have entered at 3.8% based on their own expectations about market of US interest rates. Based on all these fixed rates, I can actually derive my USD interest rate. So these are actually based on, actual transactions that happen in the market. Hence, whatever is my US amount, if it's a US dollar cash flow, it's a US dollar investment or borrowing, I accumulate or discount this based on USD SOFR interest rates. Similarly, for Euro, I use my Euro Ester interest rate because these are not risk-free. They account for the risk in my derivatives, they account for the market risk, they account for the credit risk in transactions. Therefore, I don't use US Treasury rates for discounting accumulating. I use my USD SOFR interest rate for accumulation discounting. This was all just FYI. Bottom line, you all know that practically no one in the market, no one in the industry uses government yields or treasury rates. The rates that gets used are all these proxied LIBOR or alternative reference rates or OIS rates that gets used. So for Ester, Tonar, for INR, there's MIBOR, Mod MIFOR. I showed you all the FIBL website, which gives these rates on a daily basis. All of these are the interest rates that gets used. Fair enough. Let's do the third one. Let's call that as complete market. Let me just write the definition where I can replicate any derivative payoff using shares and cash. So what complete market is ideally what we will try to prove. Complete market is nothing but any market where any derivative payoff and every derivative payoff you can replicate using shares and cash. You can create an external portfolio which can replicate, which can mirror, which can track the payoff of your derivative. That is nothing but a complete market. The next two, actually one is also fine. Next is fine. The fourth one is, let me know if you'll have any questions. I'm just going a bit this, but if you'll have any questions, let me know. Fourth one is called as self-financing portfolio. The definition of portfolio type. So portfolio self-financing portfolio where the change in the I'll copy this down and explain what I mean by self-financing portfolio. Second, guys, I'll be. Cool. Now, what do I mean by self-financing portfolio? Any portfolio of, all right, let me actually give you all an example and explain. I know if I have a portfolio of 5 shares, the value is what? 5 ST plus psi. If I go to an up move, this becomes what? 5 ST into U plus psi into e raised to R for one time step. I have 5 amount of shares into share price plus psi cash. After one time step, let's say if it's an up move, so 5 STU plus psi into e raised to R. This I already know from my previous chapters that I have. In this, can I say the portfolio value has changed? This value would have been, let's say, pi. This pi 0. This value would have been, let's say, pi u. I know the portfolio value has changed, but why has the portfolio value changed? Because ST became STU and the cash component got accumulated by e raised to R. So I received certain interest over there. Can I say the change in the value of the portfolio is purely because of my market movement? It has nothing to do with me removing money from the portfolio or putting money into the portfolio, because the values of phi and the value of psi has stayed constant. It is not like I have altered the quantity of shares that I have. I've removed certain shares or I've bought more shares. It's not even like I've added some more cash or I've removed certain cash from this account. There is no external cash flow or inflow made, but still the portfolio value has changed. Why? Because of purely investment gains and losses. Why losses? Because it can go down also. It can have pi STD also. That's a loss in that particular case. So any portfolio wherein the change in the value of the portfolio is purely because of investment gains or losses, purely because of market movements, and not because of me removing anything from the portfolio or putting anything into the portfolio, is referred to as a self-financing portfolio. Clear? Any doubts? Anyone?
Self-replicating portfolio. Like no new
Self-financing
addition,
portfolio.
no new addition or new borrow from the removal. Correct.
Yeah, yeah. Fair. If you want, I can copy this example down. I'll start with the next one, which is previsible process.
Permissible process. Huh?
Previsible process.
Pre-
PRE, previsible. Let me write it in text only. It's called as the previsible process. Any process whose value is known at step in advance and does not change over that.
Example, phi st plus epsilon is a previsible process.
Sorry.
That phi st plus epsilon, that epsilon is a previsible process, right?
Phi and psi are previsible process.
Yeah.
Yes. That is
Psi.
what my example is.
Phi
going
and
to be.
phi st plus psi is a previsible process, right?
Yeah, just phi and psi. ST is the underlying asset price. That is going to change. The values phi and psi are previsible process. All right, I'll just explain. Now, previsible process. This is a new jargon or a new concept. Let's take the example of our binomial model. 100 goes up to 110, comes down to, let's say, 90. 110 goes up to, let's say, 121, comes down to, let's say, 99. And from 99, this goes over here and this stays at 81. Now, when we were doing a replicating portfolio approach, under my binomial model, I used to compute my payoffs at this part. I calculated my equation of my replicating portfolio, calculated the value of phi and psi by solving my simultaneous equations. And that value of phi and psi, we got it back at time 110. Similarly, at time 90, I calculated a different value. Let me call this as phi 1, psi 1. We calculated different values of phi 2, psi 2 based on this payoff and this payoff. Essentially, what we are saying over here, the amount of shares and cash that I need to buy in order to replicate my portfolio at this particular time period is known to me at 110. I'll repeat. The amount of shares or cash that I need to purchase such that my derivative portfolio is replicated to my external portfolio at time whatever 0, 1, 2. At time 2 is known to me at time 1. Similarly, over here, whatever I need in order to replicate it at 99 and 81, I already know that at time 90. Similarly, at this time period, whatever are my values, if I want to calculate or if I want to replicate, I know the value of phi and psi at time 0. Can I say over here what is happening? Any process whose value, that means over here the process is phi and psi, I know the values of phi and psi one time step in advance. And I know between time 1 and 2, the value of phi and psi is not changing. Why? Because may it be an up move, may it be a down move. My value of phi and psi stood constant because that is how we derive the value of phi and psi. May it be an up move, the value of phi and psi will stay constant. May it be a down move, the value of phi and psi will stay constant. This is an example of pre-visible process. Pre-visible process is simply nothing but you know the value of the process, you know what state the value is of the process is going to be one time step in advance, and over that time step, over that one time step, the value of this process is not going to change. So it's like you know 100% prediction over here. You've done certain calculation, you know after one time step what the value of the process is going to be, and you also know over that next time step the value of the process is not going to change. Whatever you know is 100% what is going to happen. Fair enough? Understood everyone what previsible
Once
process?
again?
Yeah.
Can you once again tell? Once again?
Previsible process is nothing but one time step before I have predicted the value of this process, I have calculated the value of the process. I know that for sure over this time period, this is going to be the value and it's not going to change. So I know the value of this particular previsible process one time step in advance. I know it already before, and over this time step, the value is not going to change. So it's like saying, as an astrologer, I've made certain prediction about you all for the next 1 month. And this prediction is not going to change. I know that for sure. That's a previsible process.
Some sort of a stationary process.
Some sort of a?
Stationary process.
I mean, intuitively in English, yes. Statistically, stationary is something else. But intuitively in English, yes. It's not going to change. It's going to stay constant. Yeah, Anushka.
Means sir, we don't know if the market is go up or down, but we for sure that if it's go up, what is the final value, and if it is go down, what is the final value?
Yeah, what is the value of your phi and psi? Like, what if there is a process that has the same value, either up move, down move, and that value is already known to you today? Then yes, that's a pre-visible process.
That means phi and psi are not constant. It may change.
Or that one time step is going to stay constant. I know over here the value of phi and psi stayed constant. Over here the value of phi and psi were not the same as the up move, but in its own self they stood constant between this time. Yeah.
So sir, that means like for that particular time period, one time period, the phi and psi will be the pre-visible process that we know.
Pre-visible process. Yes.
Okay.
We
Any
wish
other
we know
doubts, guys?
we wish we can predict that one step
With certainty.
with 100% certainty.
I
At least
can
for 1 day.
I can predict. I think I can predict with fair certainty. But fair enough. Any doubts? Clear? Cool. You can copy the example down if I want, because it makes it more easier to understand. In internals, I'm thinking to keep till ETOs. Whenever internals are, that is. I'm thinking to keep till ETOs. Black-Scholes I won't keep. I know it'll take a lot of practice. I'll keep till ETOs. I can keep Black-Scholes type 1 actually. Type 1 is easy. I mean, formula is given in the table book. You'll just have to calculate.
Yeah. I mean, if you give straightforward sums, then it's easy.
Fair. But there's not a lot of variation in type 1 independently that I can ask. Okay, chalo. I think type 1 I'll keep. Till type 1 I'll keep. Type 2, type 3, type 4 I'll keep. Let me know once everyone is done. Done? All right. Let's start with, I mean, I'm putting the heading for the entire page, but we'll start with CMG theorem. Cool. Let's do whatever we need for the CMG theorem, whatever I have. There are no sums as specific that's there. This is relatively bookwork kind of question. There's derivation or theorem that you can be asked to state. There's no sum as such specifically from this particular portion of the chapter. So, as I said, or as we've seen, full form of CMG is Cameron, Martin, Kirsanov theorem. Let's see, chalo, how much we know about this. Now, can you all tell me, under my Brownian motion Ito's lemma framework, what is the SD form of share price process? DST is equal to under Brownian motion. And then we'll do it under Black-Scholes model, what we realized or what we studied. Anyone?
Mu minus sigma square by 2 dt.
Okay, that's your ST form or process form. SD form, DST. The three equations that we did in the share price process.
Yeah. Exponential.
Take care. Exponential.
X0 plus mu t.
X0.
Plus sigma BT.
Take care. The initial form. Cool. So I know after that we derived ST is equal to S0 into e raised to mu minus sigma square by 2t plus sigma bt. Perfect. That was my integral form. From this, I derive my HD form to be equal to mu ht dt plus sigma ht dbt. This is what I derived my HD form of the equation. All of this we did in that share price process, special case that we did under Ito's lemma chapter. And I also derived the distribution form wherein ST follows log normal distribution with parameter log of S0 plus mu minus sigma square by 2t, comma, sigma square t. This is what we derived. These are the three equations that we saw over there. Just give me a minute. There's a live booking that's happening. All right, sorry. I think there's just some flight that's happening in Parallel. Cool. So these are the three equations that we've looked at. I know the SD form of the share price process, DST is mu ST dt plus sigma ST dBT. I also looked at the process form, ST is equal to S0 into e raised to mu minus sigma square by 2t plus sigma BT, and the distribution form of ST. Under my Black-Scholes, all the stages I'm just making you all write so that it fits in your head, because I'm not going to write anything new in Black-Scholes. I know the only change in Black-Scholes is the mu becomes R everywhere. I know under Black-Scholes, the equation of DST that we wrote became RST dt plus sigma ST dBT. Under my integral form, this became ST is equal to S0 into e raised to R minus sigma square by 2t plus sigma bt. And finally, ST is equal to log normal log of S0 plus R minus sigma square by 2t, comma, sigma square t. Fair enough. As and when you all solve more questions, as and when you all write this equation multiple times, it'll get on getting fit in your head. Done? Cool. Can I say, under my Brownian motion, based on all these inferences, ideally, my underlying asset is growing at a rate equal to mu, because I know mu is ideally the parameter that shows me the trend. that shows whether there's an increasing trend or decreasing trend. Therefore, can I say the growth rate in my underlying risk factor is ideally mu t? And under my Black-Scholes equation, this same equation is ideally expected value of st is equal to s0 into e raised to rt. Let me write small t only, that is what we've been using. Under my Black-Scholes equation, that same mu is nothing but r. All these equations or this framework is now what we'll try to derive. Logically, you all already know why this is happening. Logically, I'm going to write a statement. Logically, under Black-Scholes framework and BSS Black-Scholes, under Black-Scholes framework, the risk from the derivative portfolio is completely eliminated, resulting in a risk-free portfolio. All right. Does this ring any bell? Our partial differential equation approach, wherein we were trying to eliminate the risk completely from our derivative portfolio in the Black-Scholes framework. Therefore, I know under my Black-Scholes framework, if the risk is completely eliminated, the portfolio has to grow at the risk-free rate of return. Therefore, logically, I know all these equations actually make sense wherein my mu has transitioned to R. Because my risk has been eliminated, it has to grow at the risk-free rate. This is the qualitative logic. We'll now do it quantitatively as to why this mu has changed to R. Qualitatively, I know it makes sense. Logically, intuitively, I know it makes sense because the risk has been eliminated. Underlying asset has to grow at the risk-free rate. Now, let's see quantitatively whether how this particular thing is going to happen.
Means sir, mu is carrying risk in that. Means if
Mu is
we-
carrying risk. Yes. Mu is not completely risk-free. It can be any trend in my underlying asset price. So let me put it that way, that Reliance, Tata and Airtel are going to have different mu's. But under my Black-Scholes framework, the risk-free rate is going to stay the same. That is not going to be different. Fair enough. I can copy this. Let's do the next part of the concept. After this, just put the title equivalent probability. Probability. Now, in order to do CMG theorem, we'll have to first understand equivalent probability measure. Therefore, we'll first understand equivalent probability measure, then we'll understand CMG theorem. me write the statement. Two measures said to be equivalent if and only if an event is probable. Measures. If probability of event E are greater than are both greater than 0, then P and Q are equivalent probability measures. Just copy this down, I'll explain. Like I said, there won't be any sum specific to this. Like they can ask in the question, state what is equivalent probability measure. So these are all straightforward bookwork related question. This chapter fairly is that everything, the numerical part is what will come in the 5-step derivation. That is also straightforward. There's nothing numerical or variation or any application based question in this chapter. They're all standard bookwork related questions that can come in. And if I was the setter, to be very honest, this chapter, I wouldn't ask for more than 4 to 5 marks probably. So one question or one sub question in any of the questions.
Which one you will ask?
I can ask CMG, I can ask MRT. 5-step derivation also, generally the entire derivation doesn't come. They can ask you any one step. So I think that's a good question to put. I can ask you any one step out of the 5 steps. That is the reason this chapter I said that it's 1.5 day for you all also to wrap it up. If you all understand it conceptually, it's just that all these theorems you'll have to remember what it is. I know this is going to get open 2 weeks before exam. This chapter at least. Cool. Now, what is equivalent probability measures? I know there are 2 measures that I've already seen, risk neutral probability and real world probability. I can calculate some event happening under P. I can calculate some event happening under Q. These are just P and Q are examples. So what equivalent probability measure is? 2 measures or 2 ways of quantifying 2 probability numbers are going to be equivalent if any event is probable under both measures. If the probability of that event happening is non-zero under the 2 measures, the 2 measures are called as equivalent probability measures. Let me take the example. All right. Let's say I calculate the probability of y'all passing FE exam in 2 ways. One way, I look at historical things, let's say. How many students have historically passed in FE? How has been the criteria? How many students failed? So on and so forth. Based on not your batch, but historically, I observe how many students have passed FE exam. That's one way. Let's say using that I got the probability 0.99. Let's be optimistic. All right. The next way or the next approach of calculating the same probability can be, I can assess historically how you all have performed in exams. I can assess how the paper difficulty was. I can assess how well I have taught you all or how bad I have taught you all. I can assess how stringent the checking has been. That's the second way, wherein all the metric, all the possibilities have been with respect to your performance and related performance. Let's say using that, the probability comes out to be, let me take this as 0.999. Let me take this as 0.8 using historical batches. Now, I know the event of you passing is probable. What do I mean by probable? It basically has non-zero probability. There is some probability of the event happening. Can I say under both approaches, under both measures, the probability that you will pass is non-zero? In such a case, both the approaches or both the measures are called as equivalent probability measure. I know there are multiple ways of calculating probabilities. If the event is probable, it has non-zero probability under any of those measures, the two measures are called as equivalent probability measure. Standalone, it's not a significant concept. When we do CMG theorem, this is a CMG actually uses equivalent probability. That's why I did this first. As to what do I mean by equivalent probability measure. Cool. If I want, I can note the example down. I'll start with CMG theorem. Let me see CMG. Let's do CMG and MRT, then we can take a break because after that we have the derivation of it, so that we can take in a flow. CMG and MRT are just theorems. There's no concept as such specific that's coming in significant, so it'll get done. Let me write what CMG is. If ZT is standard Brownian motion under P, Z tilde T is a standard Brownian motion. This is called as tilde. It's like a swiggle above Z. Is an SPM under Q, and P and Q are equivalent probability measure. Then Z tilde T is equal to ZT plus gamma into T, where this is gamma and it's a reversible process. This is SBM under P. This is SBM under Q. If I'm done, I'll explain. Cool. Now, what does the CMG theorem tell you? CMG theorem basically states that if you have a standard Brownian motion, the probability or the I know I can express any Brownian motion in terms of risk, in terms of a different measure, may it be risk neutral probability, may it be real world probability. So if I say if ZT is a standard Brownian motion under real world probability P, Z tilde T is a standard Brownian motion under risk neutral probability Q, and if P and Q are equivalent probability measure, that means ZT is probable, it has a non-zero probability of occurring under both P and Q, then you can write this relationship to hold true, wherein SBM under Q is equal to SBM under P plus gamma, wherein gamma is nothing but any constant under pre-visible process. The value of gamma will be known to you one time step in advance into the time period T. That is what the CMG theorem is. If this is true, then this relationship holds true. In exam, they can ask you to state CMG theorem. You just need to state this part, whatever is getting presented right now. Write the notation, write what the statement is, write the relationship. That is what the statement of CMG theorem is. If they ask you state equivalent probability measure and CMG theorem, write this part, write this part. Cool. Any doubts in terms of what the CMG theorem is? I mean, I know it's just a relationship, it's just an equation. It basically tells you, given your previous concepts on standard Brownian motion and probability measures, this can hold, or an equation, a relationship between SBM and the different probability measures holds true given a pre-visible process. It's basically defining a relationship. You all don't have the proof or the way in which this relationship is derived. Cool. Let me know if everyone of y'all have done copying.
So here, P and Q are probabilities.
P and Q are probabilities. Environment, like if I'm using everywhere in my pricing, like your state price deflator is under real world probability. Your risk neutral probability approach is under risk neutral probability measure. So it's just fancier word we use. We call it as risk neutral probability measure, real world probability measure, but they are ideally probability values only.
Sir, can you please explain the previous concept of P and Q?
That is nothing but in this basically case, I'm saying that your standard Brownian motion, your graph is going to exist. It's not going to have zero value. Like, all right, let me put it this way. If you are rolling a die, the probability that you will get 1 on the die, let's say you calculate using 2 different approaches. You made your own model, I made my own model. We have 2 different approaches. You got the probability value as, I know it's going to be 1/6, but hypothetically, let's say you got it 0.1, I got it 0.2. In both of our cases, we have certain non-zero probability that 1 will show up on the die. Both our measures or both our approaches are called as equivalent probability measure. But if you would have gotten the value, let's say 0, that 1 is never going to show up on the die, then it's not an equivalent probability measure. It has to have both the approaches, both the metrics, both the ways have to have non-zero probability of that event occurring. Then you can say that they are equivalent probability measures. Understood?
It's not necessary that both should be equal. It should be probable more than 0.
Exactly. That's why I'm not calling that like it's not said to be equal, but they are called as equivalent. It has to be probable under both the measures.
Means we have the 6 outcomes on the die. So in both, when you are throwing and me also throwing, so we have 6 outcomes. That is the sample place. We have the same sample place, but which one is occurring, we not sure about.
Like any event I take specifically, you calculate the probability of that event using another approach. I calculate the probability of that event using another approach. Let's say you want to know what is the probability that you will get a 1. I also want to know that what is my probability of getting 1 on that dice. You calculated using an approach, you got the answer 0.2. I calculated using another approach, I got the value 0.3. Both of our approaches hold true It's just that we have different approaches. Our approaches are called as equivalent probability measures because we have some probability of one coming up on the dice. Cool.
And this equivalent probability measure is applied on SBM. That is what CMG is.
CMGs, exactly. And it says that you can establish a relationship between both these SBMs.
The tilde is what that approximation.
Because I can't have the same notation ZT in both places, I'm calling ZT to be under P, Z tilde T to be under Q.
Basically, you want to show that this SBM and Black-Scholes are equivalent. The processes are equivalent, right?
No, Black-Scholes is not coming anywhere over here. It's between SBM only, but under different probability measures. Any more questions? Cool. Let's do the first objective of our chapter now. How did mu change to R? So I'll call that as, let's say, derivation of mu to R. Now remember, if they ask you to state CMG theorem, you don't need to do what we are currently doing. If they specifically ask you to derive, then you need to do it. But if they just ask you state, you don't have to write what we are currently deriving. Now, I know I need to start with my base equation that was originally there. ST is equal to S0 into e raised to mu minus sigma square by 2t plus sigma bt. This was my equation that I know I derived using my share price process under my Ito's lemma chapter. Now somehow magically my mu changed to R. That is what now we need to see quantitatively what this shift has been, what this change has been. First, I know there is no R. I need to introduce R. So there is only one way I can introduce risk-free rate to an equation. Multiply and divide by e raised to RT, because I know it's a risk-free rate. I need to either put it using accumulation or discounting. I need to introduce this, so I'll multiply it by multiply and divide by e raised to RT. Therefore, can I say ST is equal to S0 into e raised to 1 R I'll put inside. So R minus sigma square. Let me put R as my cursive R because there will be gamma also. So R minus sigma square by 2t plus mu t minus RT plus sigma bt. What did I do? E raised to RT that I'm multiplying, I've put it inside. Mu t, I brought it outside. And I'm also dividing by e raised to RT, which is minus RT. So I wrote that over here, and my sigma bt is as is. Fair enough. Now, can I say ST is equal to S0 into e raised to R minus sigma square by 2t. If I remove sigma common out, what do I get? Bt plus mu minus R upon sigma into t. What did I do? I took sigma common out from all three terms. Bt had sigma, so that came as this. Mu t and it don't have sigma, so I'll have to write sigma in the denominator over here, because when I multiply this, sigma will get cancelled out. And I'm taking t common out, so mu minus rt. Fair enough. Any questions? Now can you see some parallels over here? Z tilde t is equal to zt plus gamma into t. Pt plus some constant into t. So can I say this actually looks of the form zt plus gamma into t? Because zt is also SBM, bt is also SBM. I have time. Gamma is a pre-visible process. Here I have a constant. Therefore, can I write this as st is equal to S0 into e raised to R minus sigma square by 2t plus sigma p tilde t, where b tilde t is equal to pt plus gamma t, and gamma is equal to mu minus R upon sigma. Excuse me, sorry. Any doubts here? Now what happened is, can I say this is under Q? because B tilde T is ideally SBM under Q. And I also know, if you'll go to that table, if you'll remember in binomial model, we drew a table, or we did a concept of comparison between P and Q. We wrote risk neutral probability, we wrote real world probability, we proved P is greater than Q, and under risk neutral, we proved HT is equal to, S0 is equal to ST into E raised to RT. All right, let me show that also. At this comparison. Should get loaded first, yeah. So here we had done two things. P is greater than Q, and under risk neutral probability, we had proved expectation of S1 is equal to S0 into E raised to R. So I know under risk neutral probability, my underlying asset grows at the risk-free rate. That is what we proved over here. Because I know it doesn't have any risk. It's a risk neutral. It's risk-free. Therefore, now if I see my part, my underlying asset is growing at the risk-free rate. My standard Brownian motion is also under risk neutral probability. Therefore, can I say my entire Black-Scholes framework is ideally under a risk neutral framework? Which I know that I'm removing my risk completely from the portfolio. Therefore, it's a risk neutral portfolio or a risk neutral framework. That is what you quantitatively get here as well. Cool. So this is ideally what your equation is. So when we look at it overarchingly, we just actually think that there is one change. Mu is changing to R, but that's not the case. There are actually two changes. Mu is changing to R, and your SBM BT is actually changing to B tilde T. Your standard Brownian motion is changing from real world probability to risk neutral probability. There are two changes that are happening from Brownian motion to Black-Scholes. But we generally don't write that tilde. We write it as BT only because in mathematics, in our quantitative analysis, that does not make a difference. Therefore, we don't write it as tilde. But essentially, there are two changes that happen. Your mu is changing to R, and your BT is also transforming to B tilde T. Fair enough. Understood, everyone? Copy this derivation down. Let me know if you have any questions. Let me write over here using CMG theorem. Let me know if you have any questions. This they can ask you prove the change in share price process between Brownian motion and Black-Scholes framework. That can be the kind of question that can come. These are the steps that you'll need to do. Nothing additional per se. You'll start with your Brownian motion equation, bring an R, use your CMG theorem. And if they tell you state CMG theorem and prove this, then you'll have to state and then prove this particular part. Okay. lecture. चालू lecture by the way. Happy हो गया. आपके तो अटैक करना सर. रुक जाओ मेरा play. Let me know guys once all are done.
Sir, so ZT here is standard Brownian motion.
ZT is standard Brownian motion, yes. ZT, BT. So in the CMG theorem states ZT is a standard Brownian motion itself. CMG will be applicable only in the case of standard Brownian motions. And even in my case, I know BT is a standard Brownian motion. Let's take a break. After break, we'll start with MRT and the derivation. We'll connect at 9:55. Cool. Let me know once everyone is back. Your this started internship hunts. I mean, are you all open to travel or looking at places or like your cities only? Didn't think about it yet. First, milne to do, then we'll think about it whether we want to travel or not. Fair. Let me just put the thing. So called as binomial theorem. So called as equivalent cutting measure. Cool. Let's start. Now, what we'll do as the next concept is our MRT theorem. It's called as martingale representation theorem. It's also called as binomial representation theorem. It's also called as equivalent martingale measure. All three of them mean the same thing. What does this theorem state now? This theorem says if xt is a martingale under Q, and yt is a martingale under Q, then dyt is equal to phi t into dxt. Now, I can also write this as i.e. yt plus dt minus yt is equal to phi t into xt plus dt minus xt, where phi t is a pre-visible process. If you want to write this as in discrete, delta yt is equal to phi t into delta xt. And if you want to talk in terms of one time step, yt plus 1 minus yt is equal to phi t into xt plus 1 minus xt. Now, what do I mean by this particular theorem? What does this theorem states? This theorem basically says that if you have two martingale processes, we now know what a martingale process is. Xt can be a martingale, yt can be a martingale, any process can be a martingale specific or subject to it satisfying certain conditions. It says that if you have two martingale processes, then you can express the change of those processes in terms of a pre-visible process. I can basically say that dyt is equal to phi t into dxt, and I know change is nothing but what? Yt plus dt minus yt, the process value at time t plus dt minus the current process value. In discrete case, it becomes delta yt is equal to phi t delta xt. If I take one time step, it will become yt plus 1 minus yt is equal to phi t into xt plus 1 minus xt, where this phi t is nothing but a pre-visible process. You know the value of phi t one time step in advance, and it is not going to change in the particular time step. That is nothing but martingale representation theorem, or EMM. It basically helps you define a relationship between two martingale processes. Fair enough? Understood this? All right, copy this down. Again, it's just a statement, state EMM or state MRT. This is the part that you write down. Let me know if you have any question. I know after Black-Scholes, you might be finding this thoda dry as a chapter.
We thought it is independent chapter, not related to Black-Scholes, martingales and all, but still we are in all these things.
Soda independence will, like, it's not like Brownian ethos, Black-Scholes that will be there full connecting, but we'll use inferences from those chapters. Yeah. Next one. Actually, that equations we'll use everywhere. Term structure is an independent chapter. That I can say. Except for one part. Yeah. Except for one part, it's an independent chapter. Yeah, it is. Okay, like this week I don't have an election. No. Tomorrow I don't have.
Do people use all these theories and calculations while doing the investment strategies?
No, not really. So we use the Black-Scholes model. So everything actually dives down and develops to Black-Scholes only. We don't get into all this individually, but Black-Scholes, then whenever I predict something, then what is the SDA form? What is the distribution form? How do you derive the process from the SDA? How do you calculate the mean of the process, variance of the process? For that, you use the concepts of your Brownian and Ito's lemma, yes. But all these theorems, no one specifically as such puts. That's the reason all these, some of the things I've asked, like there was a workshop wherein I was thinking to revamp the entire curriculum, entire assessment, entire framework. There are different objectives that it's trying to meet as part of this change. So they are just gathering thoughts from across the globe from professionals and actuaries as to how it should be. There, I think I raised a couple of points as to like CM2, if I take example, what changes. So one of the changes was that currently the curriculum is very option heavy. We don't have any other derivative. Futures forwards, that it's one chapter, rest everything is very focused on options. So we can actually reduce that, bring in some more derivatives that are getting used practically. Some of the chapters that are repetitive, that is something that you can actually remove. Like, for example, this partial differential equation. I know it's not getting used. You don't need to have so much on it. Like introduce it, it's fine for students to know, but need not get into much more detail because you never test it and it's never being used practically directly. So all this is something that I raised, that some things can be actually removed, whatever is redundant. But let's see, I think that meeting happened in December, Jan. They are thinking about what things to do. But let's hope that by the time you all complete it, there are no significant changes.
Yeah.
But they are thinking to change the exam pattern, like exam structures also. At least that is what they are proposing. Let's see.
And the cutoff marks is what the
From
headache is.
descriptive to MCQ.
That I don't know. Paper format, I don't think they are thinking. Paper structures, they are thinking. I don't know what they are deciding. Yeah, sure. What is so?
I mean, similar to IA, if they fix some cutoff marks, then we can aim for it rather than every time it will be changing. Sometimes we get 58, we fail, 50, 57, we pass. So,
Probably, but I think, like, I personally think that changing cutoff makes sense because level of difficulty, if they put it super high, then it'll be very difficult. Like, I think CP1, they've also gone to like 55, I think.
mm,
So, but yeah, it'll become easier in easy papers because you will score good. But in difficult papers, I think it's an advantage in this case.
yeah, the difficulty will be different. Yes.
Yeah. Difficult, like those parameters can get accounted, but from a certainty perspective, yeah, can look at it. Everyone done with that inven's copy? Let me actually go. Let me know if anyone is copying. Just put the title 5-step derivation or discrete factors. 5-step discrete continuous derivation. Sorry. Sorry, I keep forgetting your exams are in May, right?
May first week. May 4th onwards is what they are proposing. 4 to 14th, I think.
I think your project's deadline, if they give it by Monday, deadline should be somewhere around 23. So I'll get 2 weeks to do the project. April, I'll take the presentation once I'm somewhere.
And I think within these 2 months, we have to give one internal internal exam, and there is a assignment 2.
Assignment as well. I think assignment internals can happen in March only. Assignment, even if they take like April mid, ideally May 4th, right? So if May 4th is what they go with, you all will get study leaves ideally from somewhere around 15th, 16th April. So they'll have to take assignment at the start of April.
Yeah.
Yeah. Are all the subjects at a good pace in terms of syllabus?
I mean, FE is okay, and even the BF is also fine to extent. We are in third unit, I think. But SRM, there is a lot to finish. Only first unit is completed as of now.
Oh,
And, yeah, only first unit we did the sums. Then second unit, I think probably will be starting tomorrow. R is going well. PTC also fine. We are in the third unit, I think.
Cool. I think PTS is not very long also. Like the MPT CAPM is actually quick. Doesn't have a lot of variation in concepts.
MPT is
So-
done. So
Perfect. Then the single index model and CAPM only. Yeah, those will get done. I think
But
those will
among these two, which is more scoring, FE or PTSA?
depends on to be very, I mean, if I talk purely in terms of ease of concepts and the depth of variation, PTSA. Because PTSA, I don't have a lot of variations. Like at then, I know if I'm asking any CAPM sum, it is going to be a variation of RF plus beta into RM minus RF only. That is one equation that you'll need to remember. There's not got like the only variation will be in terms of numbers there. In here, I can have a lot of variation in the question itself. Like your exotic option, I can make every question to be a unique question in itself. So in that way, in certainty perspective, PTSA is scoring. From an interest perspective, people generally feel like FE to be more, it's numerical, it's enough low, so that they find easier to understand, but PTSA to be more scoring.
I mean, the number of hours wise also, I think we need to spend more hours on FE. PTSA, relatively small subject, I felt like.
I think it's full 60 hours also to be, yeah, after this, I don't think it's a 60-hour subject also now. Mine was ulta, it scored FE more. Yes.
Hmm?
Mine was ulta, it scored more in FE than PTS. Because FE
Oh.
is what I found, as I said, more interesting.
Interesting, yeah.
Yeah.
People who are more
Because
interested in investment, I think they like your fee subject more. But both are in investment side only. That's
both are investment. There it's more on portfolio, front office, investment construction side of things. Here it's more on derivatives, valuation and risk management side of things. So there you are looking portfolio construction and management. Here you are looking at risk monitoring and management. So yeah, because I had started working at Deloitte like when FE started. So I think my entire thing is FE only in terms of work. So I think that's why probably.
you would have scored more.
Probably. Right. Yeah. Cool. Let's start. We'll look at 5-step discrete continuous derivation. This is the last part of the chapter. We won't do the entire derivation today, or it won't get completed. Now, what this derivation is, this is where we'll ideally solve or do the second objective of a chapter. Every derivative payoff can be replicated using 5 shares and Psycash. This is what we'll prove, and we'll ideally infer that the price of the derivative is expected present value of the payoff. Now, it's called as a 5-step derivation because there are 5 steps to the derivation. We'll look at those 5 steps clearly. We'll do the derivation for both discrete domain and continuous domain. I'll do it in parallel. You all can either do it side by side, or you all can either do one below the other, up to you. But I'm going to do both of the derivation together. Do the step for discrete, do step 1 for continuous, do step 2 for discrete, do step 2 for continuous, so on and so forth. Reason being that in some of the steps, discrete and continuous are exactly the same thing. So I'll write it as once from our current perspective. In examination, the entire derivation is very, very rarely asked together, all 5 steps. They can probably ask one of the step individually to you in the question. Because as I said, if I ask the entire derivation, ideally it'll be for a 9 to 10 marker derivation. Like even if I give 1.5, 2 mark for each step, it'll come down to like 10 mark derivation. I don't think I would want to give this chapter to be a 10 mark weightage, to be very honest, in examination. Hence, I may probably ask one of the steps individually in your derivation. For that, you will assume all the pre-steps till that particular step hold true. We'll do each of the steps, that is well you'll understand. As I said, the idea behind the derivation is that every derivative payoff can be replicated using 5 shares. You say shares, you say underlying asset, they mean the same thing. And Psycash. We'll try to prove this idea. If we prove this idea, based on this, we'll infer that the price of the derivative is expected present value of the payoff. Fair enough. This we've already seen. Now let me just write what all are the steps of this particular derivation. So we have we have step 1, wherein I'm just going to write the titles of all the steps so that we know what are each of the steps in summary whenever you all revise the derivation. If you all know the derivation, you can just revise these steps and get to know what the entire derivation is. I'll write all the steps. You all may not understand it right now, but when we do each of the steps, we'll get into each of them. Step 1 is prove that the present value of share price process is a martingale. Step 2 is nothing but the proposition step. Proposition step is basically to prove that. what I need to prove, what is that equation I need to prove. That is what a proposition step is. Step 3 will be prove that the present value of derivative price process is a martingale. I've proved two processes to be a martingale. I know the next step is apply martingale representation theorem, which is also called as binomial representation theorem, which is also called as equivalent single measure. And step 5, prove the objective. So in step 1, we'll prove that the present value of share price process, I'll do when we do it, present value of share price process will prove to be a martingale. Step 3 will prove another process to be a martingale. Step 4, I have proved two processes to be a martingale. I know it is the martingale representation theorem which defines a relationship between two martingales. So we'll apply the martingale representation theorem. Step 5 and 2 will prove the objective. Step 2 will state the objective. Step 5 will prove the objective. After this, let's start with the derivation. I think we'll complete step 1 and then we can stop. I think step 1 will get done. Once everyone is done.
Sir, what is the name of second step? Proposition step?
Proposition step. Proposition, PROPOSITIO. It's basically to prove that. Start with the
Like, if the step 5 was asked in the exam, do we need to write all the steps or only the step 5?
no, only step 5. You will assume step 1 to step 4, everything is true, and you will do the step 5. If they ask you, only step 5. Cool. Let me know once you are done. We'll start with step 1. Done? All right. Now,
Yeah.
step 1 is to prove that the present value of the share price process is a martingale. That means, can I say, first, I need a present value of share price process. So I know share price process is what? ST. That is what my underlying asset price process is what I use. They are saying I don't need to prove share price process to be a martingale. I need to prove present value of the share price process to be a martingale. Therefore, can I say I need a present value of share price process? Let us call this as DT. So I'm creating a new process DT, which is the present value of the share price process. Now, can I say I need to prove TPT is to prove that? Can I say I need to prove expectation of DT given FS equal to DS? This is what I need to prove. In other words, I need to prove e raised to minus RS into SS. This is our condition of martingale that we've studied. This is what we'll try to prove. Let's do it for discrete and then let's do it for continuous. Under discrete, I know for a binomial model, S0 can go up to US0, can come down to DS0. For one time step, right now I'm just looking 0 to 1. If I have time at time 0, the price of share price process is S0. Time 1, it can either go to US0 or DS0 because it's a discrete model. Can I say expectation of S1 is QS0 into U plus 1 minus Q into D into S0? Expected present value E of X is X into probability of X. X is S0U, D S0. Probabilities are Q and 1 minus Q. Everyone with me? Perfect. I know the equation of Q is what? E raised to R minus D upon U minus D into US0 plus 1 minus E raised to R minus D upon U minus D into DS0. If I take LCM, this will become what? Let me take S0 common out. So U E raised to R minus UD. U minus D plus D will get cancelled out. What am I left with? Right. So plus U minus E raised to R into D upon U minus D. Have I done it correctly? Yeah, I've done it correctly. Cool. Understood this till here? Fair. Now, minus UD plus UD will get cancelled out. What am I left with? S0. If I take E raised to R common out, U minus D upon U minus D. Do you all want me to solve this step by step? Or understandable? U E raised to R minus D E raised to R. E raised to R common, U minus D I have, which will get cancelled out. This we've already proved. I've just done it again over here. Didn't reference it to where we've done. But the part where I presented risk neutral probability, real world probability, there we've already done this part. Wherein I've already proved that expectation of S1 is nothing but my current asset price into my E raised to R. Everyone comfortable till here? Cool. Now, can I say this was ideally going from 0 to 1? If I go from S to T, can I say expected value of ST is equal to the current asset price, which is SS, into E raised to R, time period is T minus S. What we did, the upper proof was from 0 to 1. So I had S0 into E raised to R, 1 minus 0. Right now I have S and T. So I can say SS into E raised to R T minus S, because the basic fundamental is it should grow at the risk-free rate of interest. That is what I've done. Now, let's start with our part. Expectation of DT given FS. I know DT is what? E raised to minus RT ST given FS. E raised to minus RT will come out as constant. Expectation of ST given FS. Now, ST given FS is what? SS into E raised to RT minus S. Fair enough. I know under discrete case, expected value of ST has to grow at the risk-free rate of interest. So SS into e raised to r t minus s. E raised to minus rt, e raised to plus rt will get cancelled out. What am I left with? SS into e raised to minus rs. What did I have to prove? Expectation of dt given fs is equal to ss into e raised to minus rs. Therefore, can I say under discrete case, I proved the first thing that dt, i.e. present value of share price process is a martingale. Any doubts, anyone over here? Same concept. It's just that we are applying it onto a different thing on the present value of share price process. Let me do it for the continuous case as well. Then you all can copy it together. Under continuous case, I don't have a binomial model framework because under continuous, there's no binomial model or a discrete time step. I know under continuous, what do I have? ST follows, let's write the distribution only directly. ST follows log normal distribution with parameter log of S0 plus R minus sigma square by 2t, comma, sigma square t. Everyone knows now this from the share price process. I know expectation of ST has to be expectation of X where X follows log normal distribution. Because it follows log normal distribution. I know E of X for a log normal distribution is E of mu plus half sigma square. How do I know this? Table books. Fair. In this case, can I say it as E raised to mu plus half sigma square, which is sigma square t for me. E raised to ln S0. Can I say is S0 into minus sigma squared 2 by 2 plus sigma square t by 2 will get cancelled out. What am I left with? E raised to RT. We arrived at the same inference that the underlying asset should grow at the risk-free rate of interest, and that is what I expect as well to come because it's a risk-neutral probability. Fair enough? Everyone with me? This was for a time period 0 to t. If I have to write from a time period s to t, it will become the same thing, ss into e raised to r t minus s. Fair enough? If I look at it from a s to t perspective. Now, you're going to write the same 4 steps again. That is why I did discrete continuous together, so that you all can take a call whether to write it again. Expectation of dt given fs, I know is expectation of e raised to minus rt into ht given fs. E raised to minus rt common out. Expectation of ht is what? Ss into e raised to rt minus s. Minus rt plus rt cancel out. What I get? Ss into e raised to minus rs. Therefore, under continuous also, I prove that dt is a martingale. It's just that how do you arrive at expectation of ht is equal to ss into e raised to rt minus s is different under discrete and continuous. Under discrete, you use your binomial model. Under continuous, you use your distributional form. Everyone fair? Everyone understood? All right. Copy this down. Standalone, they can ask you prove that the present value of the share price process is a martingale. Under discrete, under continuous, you will realize from the question. You need to do this part of the derivation. Correct? Copy this down. Let me know if you have any question.
So it will be asked separately for discrete or continuous. We don't have to.
Yeah. Both won't be there because it's the same thing only. Unless, well, if they can ask you both, but if it's discrete or continuous, you'll realize from the question. And in case you are not able to figure it out, do both. Because it will take 1 minute more. Do both and come.
We can write simultaneously.
Simultaneously, exactly. Yeah. So we'll get to the rest. How I will copying? I will copying discrete and then continuous or both together.
Separate.
Both.
Cool. So let me do one thing. Duplicate the tab.
My A4 paper doesn't fit both in one side.
Yeah, fair. So let me do one thing. Uh, come over here. This will come over here. Okay. This- Let me know wherever you want to scroll. I can't see your videos for now, but let me know wherever you want to do it. I can actually see your videos. Okay, for a second.
I mean, conceptually, why we need to prove this process martingales?
That when we'll do step 3 and 4, that is when you'll realize, because everything then boils down to step 3 and 4. Step 4 and 5. Sorry, step 1, 2, 3 are used to infer step 4 and 5. Just hold on to that thought. When we do the entire derivation, I'll come back to this question.
Okay.
Like step 4, I need, in order to do my step 4, I need share price process and derivative price process to be martingales. That I've already proved before. So that way. Let me know however you want to scroll separately, discrete and continuous. I can scroll that separately. Continuous is one thing, so that you'll have. Discrete is this. Let me know once everyone is done. Next lecture, we'll complete this derivation and we'll start with term structure of interest rates.
I mean, for exam preparation purpose, I mean, how many times do you
Sorry.
revise? How many
What?
times did you how many times did you revise all the chapters for the exam?
Sorry, now you can say. I think yours was lacking for me. Say it
No,
again.
no. While as a student, how many times did you revise the chapters?
So, to be very honest, I didn't understand all these ethos and all very clearly when I was studying as a student. It actually became clear 1.5 years back when I started teaching this subject. So I think these two chapters, though, as I said, quick only, but luckily Brownian ethos was not that heavy in our exam. Black-Scholes was heavy, and Black-Scholes was because it's categorized type 1, type 2, type 3, type 4, it became easier. But at that time, I didn't understand why do we have Brownian motion. It was just alphabets only that I was writing. But yeah, it's all.
It will boost our confidence now because we also have some of the doubts here. So still we can clear the exam.
Yeah. It'll become clear. Just go on practicing. It'll become eventually clear. Keep conceptual clarity. That's it. Yeah.
Any exam preparation tips?
I mean, go on whenever you solve questions, just go on marking the ones that are very new to you or you think are important or cover a lot of concepts of the chapter. so that before exam you can just revise those sums, look at those sums, not from a learning perspective, but just look at those sums in order to revise your concepts and the variations that you were not able to solve in the first place. I think that's one thing. And the other thing is keep conceptual clarity. And know what you have to study, like what the subject contains. Yeah, broadly that. Technique. I know I'm over time. Anyone's copying? Yes. But okay. So having said that, I've been in your places. The paper worked in my favor from an understanding perspective. You can score 60 or 60, whichever. You can score good in FE2, you can score, I think. Yeah, let me see. Okay.
Only when the derivations are correct. That is
Derivations. I mean, derivations are KB. I think if I would have been the exam setter, I wouldn't put it for more than 10 marks. I mean, why only is it required? I have better things to ask. So I don't think derivation more than 10 marks I would ask.
But yeah, FM was much easier than FE.
Yeah, for sure. Just we did unit 2, chapter 2, ability measure and this pricing. We completed implied volatility part. Let me write that first. Then we did introduction, jargons, CNG theorem, MRT theorem, and step 1. Me present, Hansraj absent, Rishitej absent, Ashok present, Kaustubh absent, Riya present, Harnil absent, Yash absent, Anushka present, Abdul Rahman present, both absent, Ansh present, he was there, Upper absent, Tom present. Yeah.
Costa was there at the beginning.
Bhavani, Ashok, Kaustubh, Riya, Anushka, Abdul Rahman, Ansh, Tom. Cool. That's it. All right. Let's turn off the recording.